one on our gas unit, the first thing I want to talk about is the different phases. So we've got solids, liquids, and gas. And I want to make sure before we move on, you have a general idea of what to expect when you're looking at each of these three phases. Yes, there's technically a fourth phase, but we're only going to address solid, liquid, and gas here. So to kind of make sure we're clear on this, I've got the simulation here. So when you think of a solid, hopefully think about something like this. You've got a lot of atoms that are closely packed together. And one thing you may or may not have heard about before is that they actually vibrate. So that's why you're seeing some movement there. Solids don't sit completely still, as new as that may be for you to hear. Okay, and then liquids, what you're envisioning is this is like as if you just poured in a liquid. So what you'll see is let's start filling up the container that they're in, kind of flowing over each other. We can switch to water too to make it even more clear. So we got a bunch of water molecules there. They're flowing through over each other. They're moving about a lot more quickly and more, and they're definitely spreading out as much as they can into their container. But you see, obviously, they're only filling up the bottom part of the container since they're a liquid. And then gases is something like this. These are a bunch of water molecules, as in like water vapor. Think about gases, thinking about a lot of gases moving around, filling up the entire space, colliding into each other occasionally, randomly. They're all moving about. When they do collide, they kind of send energy to each other, and so forth. Okay, so make sure you have this idea of gases in your mind when you think about gases for this entire unit. All right, so going back to the notes here, you can draw something like that in the solid, liquid, and gas boxes there, so you have a general idea. But the first thing we're going to talk about is the kinetic molecular theory. This is a model that explains the behavior of molecules and gases in the ideal situation. There's 6 main ideas that go along with this KMT here. So the first is that gases have mass, but no volume. So what that means is they have mass, but in terms of volume, they fill whatever space that they're in. Okay, so they don't have a set volume. Fill whatever container they're in. The second one is that gases fill their containers and have collisions with each other. So when we talk about the individual gas molecules, they're going to collide with each other. The third one is that gases are compressible, as in there's some space so you can kind of compress the gases down to a smaller volume. The fourth is that gases move randomly in straight lines until they contact something. That means that they'll keep moving in the direction they're moving until they basically run into something that makes them move in a direction. And then gases exert pressure. We're going to talk about pressure a lot in a minute here. And the sixth thing is that temperature. You've never actually learned about what that is. Temperature is actually a measure of the average kinetic energy of the particles. So kinetic energy meaning the energy of movement. So it's actually a measure of how much the gas molecules are moving or gas atoms are moving around. Okay. All right, so focusing in on pressure, because we're going to talk about temperature and pressure a lot this unit, so we need to make sure we know what they mean. So pressure is defined as the force per unit area, and it results from the number and force of the collisions of gas molecules. So because the gas molecules are colliding with the walls of the container, so think about a tire, for example, the air that's in the tire is colliding with the actual tire material, and it's those number of collisions and force of the collisions that we read out as pressure. So when we think about the equation for pressure, pressure is going to be force divided by area, okay? And the metric unit for pressure, because you will see many units for pressure, is Pascal. Okay, it's abbreviated PA. So if you see anything with PA or kPa is kilopascals, you're knowing that you're talking about pressure here. All right, so atmospheric pressure, because people talk about pressure in the atmosphere a lot, atmospheric pressure is actually going to be defined as the result. So pressure that results from gravity exerting downward force on the atmosphere. Okay, so because the different parts of the atmosphere are obviously gases, there is a result of gravity pulling down on those gas molecules, so we read that out as pressure from the atmosphere. Okay, so what you're seeing here is just a column of the atmosphere. You're seeing it here drawn out with gas molecules, so the closer you get to the ground, the more gas molecules there are. That's because gravity pulls most of them down. That's also why the pressure at sea level or something close to sea level like Baltimore is going to be a lot higher than the pressure that's up in this mountain at Frostburg here. And that's also why people talk about, for example, if you follow NFL, whenever players go to play in Denver, they tend to have a lot of issues just with atmospheric pressure adjustments. So the standard atmospheric pressure at sea level, so the pressure at sea level is equal to 101.325 kPa, so that's kilopascals. One thing to note is you can see these other units, so kilopascals, pascals, we already talked about, but atmospheres, mmHg, and torr are other units of pressure as well. So you may be wondering how this is measured, especially atmospheric pressure. So it's measured through what's called a barometer. Okay, so a barometer is just going to be the instrument used to measure atmospheric pressure. Okay, so here's two examples of barometers. So mercury barometer, basically the way it works is you have mercury in here. As the air pressure pushes down onto it, it sends the mercury up the column. You measure the distance by how much the mercury rose. So you literally get 760 millimeters here when you measure from the bottom to the top. And that's why this unit is millimeters of Hg, Hg standing for mercury from the periodic table. Another type that's a little bit more common, as you may know, mercury is poisonous. There are aneroid barometers, and they look a little different. Okay, but you might have seen those guys before as well. All right, so the first thing here, we're going to get into a little bit of calculations. So Dalton's law of partial pressure, we talked about pressure a lot. This is a law that relates how the different pressures of different gases within the same container are related. So for a mixture of gases in the container, the total pressure is going to be the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 and so forth. So it's the sum of the pressures that each gas would exert if it were alone. So looking at this example here, it says the container holds 4 gases, nitrogen, oxygen, carbon dioxide, and neon. The partial pressures of the gases are 6 atmospheres, 2 atmospheres, 7 atmospheres, and 5 atmospheres, and then you want to know the total pressure. In order to calculate this, you're just simply going to do some addition. So we're going to add up 6 plus 2 plus 7 plus 5, okay? So when you do that, you should get 20 atmospheres. Your answer here, you're looking at a total of 20 atmospheres. Now, if you want to be exact, you can put the 0.00 in, like in the problem, but that's all you're going to do there. Dalton's law, pretty easy, okay? We're going to look at something that's a little bit more complicated. We're going to be talking a lot this year about this idea of molar mass. This is the first time we're really encountering it, so just a brief discussion about that. Molar mass is going to be the mass of a mole of something. So you've heard of the animal, the mole. This is something a little different. If you think about a dozen is 12 of something, a mole is a certain number of something as well, a certain quantity. We're going to come back to that later in the year, but just know right now that a mole is a unit of measurement, okay? Just like a dozen is 12. Dozen's another unit of measurement, a baker's dozen's another, and so forth. So mole is just a unit of measurement. So it's the mass that 1 mole of something has, okay? And the way you're going to do that is by using the periodic table, okay? So let's try this first problem because we don't need to calculate the molar mass on our own, and then we will try that again when we come back to it. But looking at this equation, you've got the molar mass is equal to the density, which is D. R is going to be a constant that we're going to be using a lot this unit. Okay, I'll tell you what that is in a minute here. And then T is temperature and P is pressure, as you might have guessed. Okay, so looking at these problems, whatever we see R, we're going to use this one value. Okay, so R 0.08206, and it has a whole bunch of units here. Liters, atmospheres, mole is that unit I just talked about, and K for Kelvin, okay, which is another temperature measurement scale. So looking at this first problem, what is the molar mass? It has a density of that at this pressure and this temperature. I'm sorry, that pressure. All right, so looking at these problems here, we're going to be talking a lot this unit about a new temperature measurement called Kelvin. We haven't really come across it yet before, okay? So whenever you need to use Kelvin, pretty easy to get there. You take the degrees Celsius and you add 272 to it, okay? We're going to use both those ideas here. So I'm just going to abbreviate molar mass to them then. So for this problem, the molar mass is equal to the density, so I'm going to plug in that number, times R, which is this number up here, times temperature. Now the temperature needs to be in Kelvin because this unit's in Kelvin here. So I'm going to take 25 plus 73 divided by the pressure, which is in the problem, is 1.12. So once I multiply across the top, divide by the bottom, we're looking at an answer of about 0.098, And then your units per molar mass are always going to be the number of grams per 1 mole. Okay, so that's that idea that mass is in grams, and then you've got a mole of something. All right, so let's look at the next problem. It says, what's the density of F2 at STP? Okay, now we're going to be talking a lot about this idea of STP, this unit as well. So STP is standard temperature and standard pressure. So whenever you see STP, you want to think about standard temperature is always 273 Kelvin, and standard pressure is going to be 1 atmosphere. So as soon as you see these letters, you have to think 273 Kelvin, 1 atmosphere. Okay, so that actually tells you a lot right there. All right, so looking at this, we have what's the density of F2? So F2 is going to be key. It's going to give us a lot of information. So I'm going to pull up the periodic table here. All right, so looking at the periodic table, I look for F. F is right here. F is fluorine. I look for the mass that's underneath it, like we talked about earlier in the year. Okay, so that's about 19. If you look here, I'm just rounding. Because it's F2, I take 2 times 19. Okay, so 2 times 19 is going to take me to 38. And that's how I'm figuring out what that molar mass is there. Okay, so looking at this, I know my molar mass is 38. Okay, we just figured that out. So now I'm going to start plugging things in. So I've got my molar mass is 38 equals the density I don't know. It's the same R value. And then I've got temperature. Okay, that's 273 Kelvin. My pressure is going to be 1 atmosphere on the bottom. So now I just solve for D. So when you rearrange to solve for D here, you should get about 1.696 grams per liter. Okay? If you didn't know what unit to use, it does tell you right here in the problem. It says in grams per liter right here. Okay? All right. Let's look at the next problem. So what is the density of N2 at STP? So you see those at STP again right away, 273 Kelvin, 1 atmosphere. Okay? All right, now, density of N2, we need to find the molar mass of that guy again. So looking at the periodic table here, N is right here. The number that's beneath it is 14 when I round. It's N2, so 2 times 14 is 28. Okay, so I have 28 is my molar mass, so 28 equal to D, I don't know, the same R value. Temperature is 273. Pressure is 1 atmosphere. Rearrange, solve for D. D, you're looking at about 1.25 grams per liter. And that's it. So you're going to get some more practice with this so you can try it out with your own hand here and see if it makes sense to you.